is of course closely connected to spin physics, and we explored in particular the direct product representation, and even more in particular direct product representation of spin states, and we wrote the direct product representation into a direct sum representation. We didn't quite make it until the end, so I will finish that off today. And then after SU2, I will move on to SUN in general, but in particular, I will talk about SU3, and we will find that there are similarities between SU2 and SU3. We will also have weight diagrams for SU3, but it will be 2 dimensions in which what was previously the JZ can live. Now there will be 2 dimensions and 3 operators actually. So that I hope to get to at the end of this lecture, so second half. So I want to start, but maybe let's first see if anyone has any questions. If not, then let's move on to the actual content. So what we did in last lecture was that we added spins, 1/2. So we had one spin, 1 state. Sorry, and then we had a spin 3/2. Sorry, we had 1 spin 1/2, right, and 1 spin 1. Otherwise, we would have had a complete mess. Yes, and this is why we had this 6-dimensional space with the 6-dimensional matrices, and we had direct products of stuff. And now let's try to do all this in pictures instead, and hopefully it will be a bit easier. I'm sorry for the confusion. The confusion is because I thought that this would be the example that we went through, but it's not. Here it is. It's been 1 state with 3 different states, and has been 3/2 states with 4 different states, to give us something to work on. The same method can be applied to the example of last time. So, okay, so how can we find all the reducible representation in this direct product space? Well, we will use that the J values are additive, so we can just add them. So we start by drawing one of the multiplets and the JZ value, so some M for one of the multiplets and M prime for the other. And we start with drawing it for one of them. So say that this is what the values that we have for M for one of the multiplets. So it can be +1, it can be 0, and it can be -1. So that is represented by these 3 dots here. So this goes from the J equals to 1 representation. Then centered at each of these dots, we draw copies of the other representation. So all these representations up here are J equals to 3/2. And since the spin Z eigenvalue is additive, we can get all the possible representations and all the possible Z values in this way. So, for example, we can, if we consider this multiplet, which we now have centered around this. So M is in this case 1, and M prime is 1/2, -1/2, 3/2, and -3/2. Then we get the total m by just projecting down because we have centered this, so 0 is here where we start in this representation. So this will be one option. So down here we will have 3 halves. Then we will have also for this representation centered around this point, we will have one contribution to spin Z1/2. However, that we can also obtain from this representation here centered around the 0. So we can also obtain the value 1/2 by adding 0 and 1/2. So there are 2 ways of obtaining the value 1/2. So we mark this in this diagram with a dot for the first one and then a circle for the other one. And then if we move on to the total sorry, this is my bad here. This should not be 3 halves because we have here 3 halves from here, and we have 1 from there. So this should have been 5 halves, and this should have been 3 halves by addition. Then we should here have 1/2, and then we should have minus 1/2. We should have minus 3 halves, and we should have 5 halves. With the minus sign. Okay. So the total spin of 1/2 we can then obtain in 3 different ways from these 3 different states. Similarly for the spin of minus 1/2, and for the spin of 3 halves we can minus 3 halves we can obtain it in 2 different ways. And finally there is only one way of obtaining a total spin of minus 5/2 because we have to be maximally negative both for this representation and for this representation. I should also say that the representations are sometimes labeled by the total spin, like here. This is for sure the most common way of labeling the states, but it can also be labeled by the dimension. So the spin 1 has dimension 3, the spin 3/2 has dimension 4. Okay, so in this way, we obtain all possible ways of obtaining a certain total spin Z. Then we want to find what irreducible representations that corresponds to and how many instances we possibly have of these representations. To do so, we note that this representation here with the maximal day Z value, we know that in this representation we should have all possible values starting from this 5/2 and then going down to 3/2, etc. So we must have all the states along this line. So imagine now that we sort of subtract these states from here. Then what remains is a number of dots or circles rather. Let's say that I imagine that I remove all the dots here, then I have the circles remaining and I count how many circles I have. And then I move inward and I see that here I have then this circle remaining, which I then represent with this dot. So I have another state which must be part of another multiplet because in this 5/2 multiplet there was only one instance of the 3/2 and that I counted for. So this 3/2 sitting here must be part of another multiplet. So from then, similarly, moving downwards in spin Z, I find this 1/2 state, the minus 1/2 state, and the minus 3/2 states. So, so I identify all the states within this multiplet. Then, after imagining that I have subtracted those states as well from up here, what remains is just one state here and one state here, and this is represented here. So here we should have something with 1/1/2 state and 1 - 1/2 state, and this is of course then jz or j equals to 1/2 state. So we have found that we have 1/1/2 state, 1 3/2 state, and 1 5/2 states. Which we can also express as this. So 1 tensor product or direct product, 3/2 is 5/2 plus 3/2 plus 1/2. And in doing this sort of exercise, it's also very useful to check that the dimensions add up the way they should, because then you have most likely not missed anything. So here, for example, the one state, it's been one state, there we had 3 states. The spin 3/1/2 states, there we had 4 states. And then this should equal the number of states in the 5/2 representation, so that is 6, plus the number of states in the 3/2 representation, that is again 4, as here, and the number of states in the 1/2 representation, so that is 2. And now 3 times 4 is 12, and that is indeed also the sum of these numbers. So we are unlikely to have missed anything, so it's with a very high probability correct that this is what we get. Any questions to that? Okay, then here we have explored it in a special case, but this can be done in general. And in fact, it turns out that if one considers the tensor product of 2 irreducible representations, dj1 and dj2 of SU2, then we have decomposition that the tensor product between dj1 and dj2 is a direct sum over different representations, dj, where j runs from j1 minus j2. So in our case, this was then 3/2 minus 1, so it should have run from 1/2, and this is indeed what we found as well. We found no spin 0 representation up to j1 plus j2, so 3/2 plus 1 equals to 5/2, so this is indeed what we found. And if you look at this, you see that there is no coefficient here in front, so we only have this representation for each possible j value appearing once here. So we cannot have 2 spin 1/2 representations, for example. That this is the fact that we can at most have 1 is something that one can prove, and the proof is written here, but I think it's a bit too lengthy to spend time on, so I will ignore it. So let's see again if there are any questions to this. If there are no questions right now, I like to recapitulate what we have done both last time and today. So I'd like to say a few general words about the procedure of working out irreducible representations. So we want to go from a product representation to a sum representation. And quite generally, and if you go back and think what we did last time, you can see that that is indeed also what we did. So quite generally, we start with combining the states with the largest m. So the eigenstates of the direct sum representation with the highest possible j value, j1 plus j2. There will only be one such state in that multiplet, because there is only one way in which we can obtain the total spin Z, that is by picking the maximal value for both this guy, from both this guy and that guy. So we will have one such state with this total spin and this eigenvalue of m. Then what we did last time was that we used the lowering operator on this product space to get all the other states in the same irreducible representation. So in the example we just went through, that would have been in the 5/2 representation. And then after that, and then we move down to the next representation, and that would in this case have been 3/2, and then we would have found all the orthogonal combinations to the state where this is lowered once. So note here that this state is that state, but with the eigenvalue being 1 unit lower for Z there. So we had one such total Z eigenstate in the multiplet up here, but we should also have one in the multiplet with J being 1 lower. And this we then find. So we pick an orthogonal combination, and since there is only one representation with the second highest J, we can do it in a unique way up to a sign, or in principle a face, but it's only annoying to carry around faces, so we don't do that. And we pick the plus sign as well, but we could have done something different. Okay, and in this way, one finds all the states in the J1 plus J2 minus 1 representation, so in the second highest representation, by acting with the lowering operator. And then when all states in the J1 plus J2 minus 1 representation have been found, we go one step further in the total J and find all the states in the next representation. And then we iterate like that until eventually we reach the lowest possible J quantum number and found all the states within that representation. Okay, so if we go up and look at what we did here, this here was actually a rather easy and convenient way of finding all the representations. But of course, it didn't tell us how the change of basis matrix looked. So the change of basis between the direct product basis, which is obtained according to the direct product recipe, and the block diagonal direct sum representation. Now, the coefficients in that change of basis, that is nothing but the well-known Cauchy-Gordon coefficients that you should have encountered in quantum mechanics. And in general, the identification between the basis vectors in the product space and the basis vector in the irreducible representations are given by these Cauchy-Gordon coefficients. So if we have two different bases, so one being the direct product basis given by J1 M1 and J2 M2, and one being the direct sum basis, the basis that we actually want to have with a block diagonal structure, then the direct sum basis or state in that basis is given by summing over all M1s and M2 that can contribute to this particular J and M. And then we have a coefficient. So this is the Cauchy-Gordon coefficient that depends on the total J, this J here, J of the first starting representation and the J of the second starting representation and of all the M's. So the total M from here and the M's that we pick out in the respective starting representations. So the point is that this state can be written as some coefficients times that state, and then we can also use another notation for this. So instead of the direct product, we can write here J1, and then M1, and then J2, and then M2. And since we require both these bases to be orthogonal, so both the direct product basis and the direct sum representation, they should have orthogonal bases. So we can find actually coefficients by calculating a scalar product. So this Cauchy-Gordon coefficient from up here or from up here is given by the scalar product between the state of of the total M and this state from here. So it's nothing but a scalar product. So I want to make you very aware that what we are doing here in this fancy Cauchy-Gordon decomposition is actually nothing but a change of basis. We are only changing the basis. I think that is something that is not stressed to a high degree in quantum mechanics courses. Maybe you had a better one, I'm not sure. Okay. And then also using the bases, both bases, orthogonal, we can find that the inverse transformation matrix or inverse Cauchy-Gordon coefficients. Cauchy-Gordon coefficients are then the coefficients in the change of basis matrix. And if we want to go to a state J1, M1, J2, M2, then we can do so by just inserting a big 1. And here we get back the state J, here we get the state Jn, from which we want to form linear combinations. And here we then have the coefficients in that inverse transformation. And the Cauchy-Gordon coefficients for SU2, they can be calculated in general, and they can be written in a closed form, although it's very complicated. And if you look into the various sources, various literature, you will find all sorts of different notations from them, so be aware of that. So we will here use the notation of J1, J2, M1, M2 for the starting representation, and then Jm for the final representation. But there are also other representations that can be found. If we would then go back to the first example that we considered last time, where we had a spin 1/2 times a spin 1, so something with dimension 2 times 3, which we then reduced to something with dimension 4 plus something with dimension 2. If we go back and compare, we can read out the Cauchy-Gordon coefficient for that transformation. So I'm not going to do it, but really if we have a look, we see, for example, we have a look here, and we can pretty much ignore the first information here because that's just the total starting spin, so that was always the same. And similar this then we saw that if we had the spin if we wanted a state with total spin 3, then we could obtain this state by adding 1/2 and n, and we could actually only obtain it in that way, so that coefficient must be 1. And if you go back and browse back into the previous pages here, you can identify the total spin up 1/2 in the spin 3/2 representation and see what coefficient we had from the first spin being -1/2 and the second spin being 1, and we get something. And then this very state also had a contribution from where the first spin was 1/2 and the other was 0. So if you want, but I'm not sure I suggest it because it's a bit tedious, but if you want, you can go and check all these coefficients in the previous example. And as I mentioned, it's also possible to write down a closed form for the Clebsch-Gordan coefficients, but we're not going to spend time on it because it's not worth it. It's not that interesting, and it's a long derivation. So I will move on to slightly different topics. So let's see if there are any questions before. If not, then that concludes the direct product representation, and I will now say a few words about the so-called reality property of SU2. And in many places in these notes, I leave stuff in gray that I don't go through because I think, well, at some point we have to prioritize. We cannot make it all, but it's nevertheless interesting and fits very well into the content. And what's left out here in gray is the Lie algebra in the mathematician's choice. So we will not go through that, but we will go through the same thing in the physicist's choice, where we have Hermitian generators. And we will then talk about the concept of representation being real or pseudo-real. Before going there, we note that if we have a particular Lie algebra and we have some commutator relation, such TA commuted with TB is I, this is choice, structure constant FABC TC. Now, if we take this relation and we complex conjugate it, so we then see, so we just take the star of this thing and the star of that thing, then the I goes to minus I, the FABC stays FABC, and the TC becomes a star, TC star. So what we then have is the commutator between the complex conjugated representation is IF ABC, and then this minus sign I just multiply in here with the TC, so it's TC star. Now all my generators have a star, but only one of them has a minus sign, and I have the right constant in form, the FIBC that I want because I want this Lie algebra. But if I insert a little -1 here and a little minus sign there as well, such that I instead consider minus TA star commuted with minus TB star, and this is IF ABC minus TC star. So now here I have exactly the same equation for the algebra as here. The only difference being that I have a minus and the generator complex conjugated, but I have that in all three places. So, and from this, we then see that this minus TA star is actually also a representation because it satisfies the commutator relation. It has the same algebraic structure. So the other representation denoted by TA with bar here, another representation is obtained by taking minus T star. And this is known as the complex conjugated representation, because if we take the original representation and complex conjugate it, we get this thing here. So let's check that. So we have e2 minus e2 minus I alpha ATA, so e2 a general linear combination of generators. Then we complex conjugate it, so we have obtained a plus sign there. This plus sign we write as one minus sign in the front and one minus sign in front of the generator, which of course also was complex conjugated. Then this thing here is then nothing but our complex conjugated representation, and it satisfies, it generates the group in exactly the same way with the minus sign there. So the whole point is that having one representation, we can obtain another representation, the complex conjugated representation as well, in a completely foreseeable and general way. Now, one option is that this complex conjugated representation is related to the original representation with a similarity transformation. So the conjugated T's are then of the form S, T, S inverse. And if we want to call it a real representation, we require that S transpose is S here. So if we have this relation at all without any constraints in S, then we have a similarity transformation between the representations and they are one-to-one. We do not always necessarily have that because complex conjugation cannot always be put in the form of similarity transformation. But if it can, and if we have this property that for the change of basis matrix, that S transpose is S, then we say that we have a real representation. If instead we have the same sort of relation, but with S transpose being minus S, then we say that we have a pseudo-real representation. That is sometimes also called like a quaternionic representation. More generally, if we have this sort of relation, but where S does not have either this form or this form, we have a complex representation. And then actually in the case of SU2, which we have now studied in quite some depth, it is the case that we only have real and pseudo-real representations. So to argue for that, we would then want to find, for example, for the spin 1/2 representation, that the complex conjugated representation can be related by a similarity transformation of this form where S transpose is minus S, that we can find such a transformation. So we then take the 1/2 representation of the case generates, and this would then be sigma A over 2, that was what we had. And now we complex conjugate it, and we should then check that this thing can be obtained by some matrix inverse, which has the property that that matrix transpose is minus itself. And I am not going to go through straightforward matrix multiplication here, but you can do that, and you will find that matrix sigma 2 does the job. So sigma 2 can be used as S, showing that this is a so-called pseudo-real representation. And similarly, actually, one can do that for the spin 1/2, so they equal to 1 representation, where we at some point had this form of the generators. If we want to find a complex conjugated representation, which was obtained by inserting a minus sign and a star, then that thing should be obtainable by some matrix, the original stuff, the transformation matrix inverse, where this S should be symmetric. And here it turns out that this S does the job, and it is indeed symmetric. Yes, I'm skipping the steps here. It's not worth going through them. So do we have any questions to that? Okay. So then I like to make a little remark on the connection between the group SU2 and the group SL2C. And the remark is quite easy and quite fundamental. And we will come back to it when we talk about the Lorentz group. And the point is just that if you take this of SU2 and you allow for complex coefficients multiplying these generators in the exponent, then we will break the unitarity. We will no longer have Hermitian generators, the physicist's choice. But the tracelessness property, so as in trace, as in determinant 1, which at the generator level translates to the generator being traceless, that condition still remains, because if you take a traceless matrix and you multiply it with a complex number, it's still a traceless matrix. So SL2C can then be generated using complex linear coefficients, but otherwise the same generators as SU2. And actually, we have already encountered some operators which we alternatively could see as generators for the SL2C space. So instead of the essential sigma 1, sigma 2, and sigma 3, we could have taken J plus, J minus, and J3, allowing for complex coefficients. So that would also do the job. So before, in the SU2 context, when we were introducing operators J plus, J minus, and J3, we could have viewed it as if we used the SL2C generators all the way along. So that concludes what I wanted to say about that. And it actually also concludes what I wanted to say about SU2. So let's see if we have any questions to that before we increase the dimension. No questions, then we move on to higher dimensions and SUN. You should thank Hugo for all attempts of being funny in this text, not me. Or blame him, whatever you prefer. The power of the sun. Okay, so we want to now consider special unitary n times n matrices, or the corresponding groups, the groups that can be defined in that way. So we start out here with the Lie algebras of SUN. And now we have seen in exercise that in the physicist's choice, they are generated by Hermitian matrices. And Hermitian matrices, of course, have the property that lambda dagger lambda implies that if you consider the ik component and complex conjugated, it's the same as lambda component ki. So wanting this property of the generators, we have that the elements in the matrix must satisfy this property. So for example, if we take some general parametrization of some element, let's take lambda 32, and we let it be r plus is for some real numbers r and s, so it's a general complex number here. So we put this here, then the hermeticity constraint implies that here we have r minus is. And we can further decompose this matrix as r times a matrix with almost only zeros, but in opposing places a few ones. And of course, similarly, for the imaginary part here, we have the number s times this matrix with almost only zeros, but in a few places minus I and I. And in fact, any Hermitian matrix can be constructed by real linear combination of basis vectors on this form. And some diagonal ones. So here we have the diagonal ones. So we have 1 in some place and all other zeros. And we place the 1 in all possible places. Then we had those that had a real number in opposing places, and here we have to consider every possible place of having these real numbers. And similarly, we had minus I and I in all opposing places, and we have to consider all such matrices. Actually, if we would take all of these, this would generate U, and so just unitary, not special. If we want special matrices, we should have that the determinant is 1, and we should have that the generators are traceless. This matrix here, for example, it is not traceless, and none of the matrices here are. So the trace of those matrices are not 0. So they will not generate special matrices. But we can simply form linear combinations of them, giving us traceless generators. So if we just take this guy minus this guy such that we have this matrix, etc., we will have a set of traceless, another set of traceless Hermitian generators. Furthermore, we will have found a general parametrization of the generators of SUN. So up here for UN, we should have n squared matrices, and it's easy to see that we have that. We have n from the diagonal ones, and then we have n squared minus 1 from the off diagonal ones, because although say this element is correlated with that element, it is compensated by the degree of freedom that we obtain from this matrix with the minus I and the I there. So we have n squared generators, and then avoiding the linear combination giving a non-zero trace, we can take, for example, these generators here, and those generators combined with the lower 2 rows here will then generate SUN matrices. So we have then found a general way of generating SUN matrices, and it's 11 o'clock. So let's see if we have any questions, and then we take it to break. Okay, so no one seems to want to ask anything. Then I suggest to take the break, and I stay here and see if someone wants to ask me in a smaller context. So no questions. Then I will also take a break and come back a few minutes before we start, see if something has appeared. This is just to say that I'm in front of the computer if someone wants to ask. So it's time to start again. Maybe let's see if we had any questions surfacing during the break. If not, we will move on. So we were in the process of finding generators to the group UN and SUN. We had just found that we can write them as linear combinations of these matrices here. And we also want to persuade ourselves that we actually have an algebra here. So let's have a look at the generators. So to be an algebra, we must have the property that if we take linear combinations, we stay in the algebra. And if we take the commutator, we stay in the algebra. And it is quite easy to see that this is the case. Because for each of the matrices, we had it yeah, okay. So we are, of course, I was not quite clear here. So these summation matrices, they are the physicist's choice. Now, if the algebra is actually not physicist's choice because then in the commutator we have this little I. The algebra is the mathematician's choice without the I in the commutator and with anti-Hermitian matrices instead. So the anti-Hermitian matrices are, of course, trivially obtained from these Hermitian matrices. So let's assume that we have essentially multiplied with I to make the matrices anti-Hermitian instead. So A dagger is minus A. Then if we form a linear combination of matrices A and B with this property and take the dagger of that, then since each A separately goes to minus A and B goes to minus B, then clearly the linear combination is also anti-Hermitian, so one box ticked. Then we want that AB dagger should be minus AB, so we want the commutator as well to be anti-Hermitian, and it's easy to see that it is. So if we write this out, this is AB minus BA dagger. So when we dagger, we reverse the order. So it is B dagger, A dagger minus A dagger, B dagger. We have the anti-hermeticity relation. So we pick up a minus sign from A dagger. So A dagger is minus A, but we also pick up a minus sign for B dagger. So we pick up two minus signs there. And then we can cross out the daggers. So we then have that this is BA minus AB. So it is minus AB as it should be. So the commutator is anti-Hermitian, so we stay in the algebra. And taking all the matrices, we have the UN algebra, and if we confine ourselves to matrices which are traceless, we have the SUN algebra. And it appears to be some sort of typo here because it should not be UN in one place and SUN in one place. So the SUN matrices have traceless generators. So I should fix that. Of course, tracelessness is also trivially reserved for a linear combination. Okay, if we want to be more specific, we could take Hermitian matrices. We essentially multiply with I to get anti-Hermitian matrices, but in all other stuff they are minus the minus sign in the factor of 2. That is just convention, and this area is plagued by convention. So I think the best strategy is not to worry too much about minus signs and factors of 2 and i's only when you have to. Of course, if you take the generators and make them twice the size, you'd still generate the same group. Now, if you multiply them with a minus sign, nothing essential has changed. Now, we want to restrict ourselves to the anti-Hermitian matrices with trace zeros or vanishing trace. Now, of course, if we take linear combinations of those, we still have a vanishing trace, but we should also explore the commutator. And for the commutator, we note that the trace of the commutator vanishes because the trace is cyclic. So the commutator would be something like trace AB minus trace BA, but that's traceless because the trace is cyclic. And we have seen already that the trace is that the commutator is anti-Hermitian, and if we combine this, it implies that we stay in the algebra also for the case of SUN. So we have learned both how to generate SUN and how to generate UN. And we may insert possibly an annoying factor of 2 between our traceless Hermitian physicist matrices and the anti-Hermitian mathematician generators. I think don't spend time on exploring the factor of 2. It's not interesting. The reason that I nevertheless choose to keep it here and not to keep it out is that it is the most common convention. So if we are considering the structure constants of SUN and in particular of SU3, we will have a commutator of lambda, so we will have a factor 2 in the commutator relation defined in the IJK. So of course, with this additional factor of 2 here, that goes through, and if you then want the anti-Hermitian mathematician conventions generators to satisfy this constraint, you will have an additional factor of 2 for the lambdas here. Okay, so here we have what is actually the algebra, and here we have what pretty much every physicist would use. And the physicist would also call this an algebra, and I'm extremely likely to do so because this is what I hear all the time. But one should be aware that these lambdas in principle do not form an additional algebra because we have an I here that would spoil the hermeticity property. So these are technically, from the mathematician's perspective, not the elements that form the algebra. Then the matrices can be normalized, and we will get back to that later on, and we have already seen it actually for SU2. So we have taken traces of generators, and one way of defining the concept of orthogonality is to take the trace over generators. And if we take trace of the matrices that we have encountered before, they have the property that they are orthogonal with some annoying factor here that I would be happier without. What we will use the trace for, though, is to compute the structure constants. And we will find that the structure constants, which we have previously found to be antisymmetric in the first two indices, because they were defined as a commutator which is antisymmetric in those two indices, we will now prove that they are actually antisymmetric in all the indices for this case here. So we will, so to prove that, we take the algebra relation. So then we have that lambda I k was 2I c I k m lambda m. So the stuff and circle in red was that equation. Then I multiply it on both sides with lambda L, and then I take the trace of it. So that equation does hold, it comes from the algebra. Now taking the trace on this side here, I see of course that my 4 factors just are just pulled along, and then I had chosen my lambdas such that they were orthogonal. So I had chosen trace lambda I lambda k to be 2 delta I k. So in this case I obtain delta m l because I have m and l here. So identifying m and l, I have 4I c I k l. And this then means that I have a relation between my c I k l and this trace here. So my c I k l I get by dividing out 4I, so I have 1 over 4I, and then I have this trace standing here. So I have a trace over a commutator and multiplying with another lambda matrix. And now just writing out the commutator, so I have trace lambda I lambda k lambda l here minus trace lambda k I swapped places and lambda l. Now recall again that the trace is cyclic. So I can move the elements here from the left to the right as I wish. Or more specifically, I can swap if I want place of the k and the L here, and not only the I, for the I and the K. So the first two indices we had seen before, that we had something that was antisymmetric because it came from the commutator, which is antisymmetric. Now we see that we can move indices around here. And we obtain this relation here. So we have actually that any odd permutation of the indices will change the sign. So I can swap any two indices here, swap the order of those, and I will get a minus sign for the structure constant. Now, in particular, this implies that CIDK is antisymmetric, is 0 if two of the indices are the same, because if I swap the position, I should have a minus sign. Well, the only quantity fulfilling that is 0. So those are totally antisymmetric. So in the non-vanishing interesting structure constants, we have no index appearing more than once. Okay, any questions to that? If not, we will move on to the SU3 group. So SU3 is the group associated with the strong force. And it is actually where I have spent most of my research career so far. Despite that, the level of detail in these notes is not something that I could advise you to study. So this is my field, but I anyway think that Hugo, who originally wrote this note, is spending far too much time on QC. So if I say so, probably pretty much anyone would say so. So when you browse these notes, you will see that there is a lot of gray commented out stuff. And this is because I think it's not that important. We have more important things to do. It's more important that we can explore the Lorentz group and the Poincare group relevant for space-time. And it's more important that we have a go at classifying all so-called simple and semi-simple Lie algebras. And if one wants to study QCD in detail, I would not actually advocate this multiplet pictures as you will see them in this in the notes here, where one is looking at the individual states. Rather, one should use Younger diagrams to explore the representations of QCD. It's much more efficient, and all the details that we will see when it comes to multiplets is less relevant than it could be for the reason that we don't observe color. So in QCD we have confinement, so we never measure that we have a red or green or blue quark, so-called red, green, and blue. And therefore, since that will imply that we can always sum over color, because any observable that we will ask for is a color sum quantity. And that implies that a lot of detail of the multiplets that we will come to know now is not that interesting. I mean, it's of course a theoretical description of nature, but it answers questions that we can never answer experimentally. So in the SU2 analogy, it would be like never not being able to measure spin Z. And if we couldn't measure spin Z, it would be slightly less relevant to do the spin Z decomposition. Okay, so after this introduction to SU3, really important for the strong group, we move on. So we will now have a rather detailed look at the SU3 algebra. So first to remind you, the group SU3 are the groups that satisfy G dagger equals to 1 and are in S, so they are special. So if we want to view them as a restriction of SL3C, we constrain SL3C by requiring that G dagger is equal to 1. So they could be special and unitary. And as we have seen in one of the exercises, we have n squared minus 1, and that is 8 in this case, independent generators of the SU3 algebra. So here we have a lot of matrices. In fact, more than 8, and I think it looks a bit like a mess. But let's try to see through the mess here. And of course, there is a good reason why all these 10 actually matrices are defined. Although only 8 of them will be independent generators, the others fill a purpose as well. Okay, so let's have a look at what we have. The generators here, we label them by lambda. And what lambdas can we have? Well, we can have lambdas where we have essentially placed the sigma matrices in different parts of the 3 by 3 matrix. So we can have sigma 1, sigma 2, and sigma 3 placed in the upper left corner, or we can have it placed in the lower left corner, or we can have it scattered out over the 1 free component, so it consistently zeros in the middle. That gives us 9 generators. We only have 8 independent ones, so we will not use all of them. The ones that we will use, and this is pretty much always the conventional choice, is that we will use the first three ones with sigma 1, sigma 2, and sigma 3 sitting in the upper 2 by 2 block. Then we will use this guy with the -1 and a 1 in the 1 free component, similarly with the minus I and an I. This matrix we will not count as one of our generators, but we will use it, so it makes sense to define it. Then we have sigma matrices in the lower right corner. And there we will use the one with sigma 1, that will be one of our generators, the one with sigma 2, that will be another one of our generators. We will not use the matrix with sigma 3. And actually instead, so we will not use these two matrices here. Using them would give us 9 generators, crossing out both gives us 7, so we want one more matrix. The matrix that we will use is this matrix here. The reason for choosing this matrix and not the one of these is that in a sense it is orthogonal to that matrix. And well, in what sense? Well, one sense is the trace condition. If you trace this times this, you will get 0. Another sense will be in the weight diagrams, so we will come back to that. So for SU2, we saw that we have multiplet states and we label them along, we arrange them along some line which measure the Z. We will do this essentially the same thing for QCD, but we will need 2 directions. And actually one of them will be T3. And the orthogonal direction will be given by the Y. But now I'm going ahead. But this is the motivation for using these matrices here and that matrix here as our independent generators. Okay, now some more annoying factors of 2. Although the lambda 8s are often called the generators, we could have had a normalization without these 2, and I think that is the most sensible convention, but it is not the most used convention. The lambdas are very often defined like they are here in the majority of all cases. However, it is also custom to define lambda A over 2 and call that TA and call the TA the generator. So this is what you will see in QCD pretty much all the time, but not all the time, not if I'm the author, but most often. Then, since we had that the rates of lambdas was normalized to 2, and now we're making them both a factor 1/2 smaller, so we will have the normalization of 1/2. So trace TA if you want, TA if you want, TB rather, is then 1/2 delta AB. So for those that may come in contact with QCD, this is definitely the most common convention. And we also then write the commutator, and now we can write it in terms of the T's instead. So we have then the commutator of TA TB is I FABC TC if you want, where we have just argued that this FABC is totally antisymmetric. And having the form of the matrices here, it is entirely straightforward to calculate F1, 2, 3, etc. using one of these equations here. So it is just to multiply out this commutator and identify coefficients in front of the matrices. So that is very easy and straightforward, and I will not do it, but if you look at it, you can see that they have different values. So F1 to 3, for example, is 1. All of these matrices up to a sign is 1/2, and then we have the structure constants involving the odd guy here. So the lambda 8 also has an odd size, 3/2. Aside from a possible normalization issue, the labeling of generators is pretty standard actually, so you will most likely find it being exactly like this, apart possibly from the phi-2. Okay, now let's come to something pretty essential. So I want to talk about the concept of a rank. We say that SU3 is a rank 2 group. That means that it has two simultaneously diagonal and thus commuting generators T3 and Y. So going up to the matrices, we see here that our T3 up here is diagonal and our Y up here is diagonal. They are diagonal and that's nice because then they commute. And that's nice because then we can simultaneously label states according to the eigenvalues of them. However, we cannot find another simultaneously commuting or simultaneously diagonalizable matrix. So we cannot rotate and change bases here in such a way that we find a third commuting generator. There's only two, so we have a rank 2 group. And the commuting generators are said to form the so-called Catan subalgebra. And we will explore the Catan subalgebra and we will explore the states in the space of simultaneous eigenvalues to these operators. So that will be the analog to exploring the spin Z eigenstates. Okay. One thing that will make the analysis here quite a bit easier is that it's very easy to see that this SU3 algebra actually consists of 3 SU2 subalgebras. Later on, we will come back to this statement that they are not invariant. The algebra is simple. That essentially means that you can, if you multiply, if you do a similarity transformation from the SU2, SU3 group, you will mix them, so we don't have an invariant subalgebra. Let's get back to that later. Okay, so now if we go back and take a look at the matrices called T, V, and U. So we are then using all these matrices here. They are all our T matrices and they have sigmas in the 1, 2 components. Then the V matrices, that is these matrices here, including the V3, although we don't call it a generator. These matrices have sigma matrices in the 1, 3 components. And finally, we have the U matrices. These matrices have sigmas in the 2, 3 components. And of course, if we look at say this set of generators, the T generators, since we have zeros here and only have something here, and in those places in the 1, 2 components, we have exactly the sigma matrices, so we will have exactly the commutator relations that we know from SU2. So those will give us 1 copy of SU2, those will give us another copy of SU2, and those will give us yet another copy of SU2. So the T's, the V's, and the U's give us 3 different but dependent copies of SU2. So we do what we did for SU2, and we define raising and lowering operators. So we have T plus minus being T1 plus minus IT2. We have V plus minus being V1 plus minus IV2, and we have U plus minus being U1 plus minus IU2. Then, of course, by construction, by the shape of the matrices, if we consider only this block here, this is exactly 3 copies of SU2. However, as mentioned, these copies are not independent. And furthermore, while the U1 and U2 and V1 and V2 were taken to be generators, we did not include these among our generators. So we rewrite them in terms of actual generators. So this is done here and this is done here, and it's very easy to verify these rewritings here. So I will not do it. Okay, so the point is that we have them 3 copies of SU2, but they are dependent. One can also, and this is again completely straightforward matrix and multiplications, verify the following commutation relations. So we have the T3 and U plus minus don't commute, but gives us 1/2 U plus minus. We have the T3 with V plus minus don't commute, but give us plus minus 1/2 V plus minus. We have the U and Y don't commute. Y and V is also not commuting, and P and Y, however, are commuting. So in a sense, they will turn out to be orthogonal, as mentioned before. Now, if we take a look at the commutation relation between the T's and the V's, the T's and the U's, and the U's and the V's, and if we take these particular combinations, they are 0. Some other combinations, T with me minus and T with T plus with U plus, and U plus with me minus, they are not 0. So there's some sort of difference between these different sets. And that difference will soon become clear, because in a sense, these will form an angle of 60 degrees, and in the same sense, these will form an angle of 120 degrees. Also, the hypercharge Y, it's called hypercharge, is not commuting with the U's or the V's, but we have some commutator, but it is commuting with T's, and this is why it's nice, because they are simultaneously diagonalizable. The set of commutation relations here is not complete, and more commutator relations can be obtained by daggering the equations. So the dagger of T plus is T minus, and the dagger of V plus is V minus, as for the SU2, or what they were called L plus minus and L3 / LZ instead. Okay, now to the step operators in SU3. So for SU2, we had that the multiplets were labeled according to the eigenvalue of the Casimir operator J squared, not it being in the algebra, and the generator J3. So we cannot find any other element in the algebra commuting with J3. So SU2 is then a rank 1 group. SU3 is rank 2 because it has two commuting generators, and actually it also has 2 independent Casimir operators, although we are not spending time on that. So those states, Casimir operators and J3 and Y could be used to completely characterize the SU3 multiplets. But instead of the Casimir operators, we will use some other quantities, P and Q. This is pretty analogous to SU2, where we used J rather than the eigenvalue of the Casimir operator to denote the eigenstates. So actually one thing that is a bit different and a bit redundant to the SU2 case is the labeling of the states. So we did not count U3 and V3 as our independent elements in the algebra. However, we can form those states as linear combinations if we want. And if we go back and have a look at the V3 being diagonal, the U3 being diagonal, and the T3 being diagonal, we see that they are all diagonal, so they do all commute with each other. So we can label states using the information of these three operators. Doing that, and that is what we will do, will not give us will give us redundant information because they are linear combinations and of independent quantities. They are not independent themselves. So we will, but nevertheless, it's not forbidden to use this redundant information to label the states. And so we will do that to see what we get. Okay, so we will label our states T3, U3, and V3. And we can then write that T3 acting on the states gives us the eigenvalue T3, U3 acting on the state gives us the eigenvalue U3, and V3 acting on the state gives us the eigenvalue V3. And here there are hats over the operators to denote that they are in some particular representation. So rather than writing out this clumsy notation, we are using just a hat. Okay, and now we will explore the action of the raising and lowering operators on the eigenstates. So first we act with T3 hat, or I will just call it T3 on the plus minus on this state. And this is exactly analogous to the SU2 case. So there, this guy was called L3, and this was called L plus and minus. And after a little bit of algebra that is written out in detail, so you can just replace the T's with L's in your head if you want, and you will, by exactly the same calculations as before, be able to see the T3 acting on the state which has already been acted on by T plus or minus will give us T3 plus minus 1 times that state. So same state there and there. So this state is an eigenvalue of T3 with eigenvalue T3 plus minus 1. So it is thus a raising or a lowering operator. So this state then has T increased by 1, but that's what we learned. We don't know what happened to U prime and V prime here. Maybe they are also changed. They will be changed actually. And then we could have some different normalizations in principle here as well. To see what happens to the U3 eigenvalue, we act with the U3 eigenvalue on this state. Then we do the same tricks as before. We write u3 t plus minus as the commutator, giving us those elements in the right order, minus them in reversed order, which we compensate for by this term. Then we let this term stand, and we use that this commutator is minus plus 1/2 t plus minus. That identity is also something that is straightforward to derive using the matrices. Now, we are in a position to pull, so this U3 gives us then an eigenvalue U3, and after that we are in the position to pull this t plus minus to the other side, so it ends up here. So it's already standing alone, just multiplying a constant, which ends up here. So the wisdom learned from this is that when we have acted the U3 hat on this state, we have recovered that the U3 eigenvalue has changed when t plus minus acted on it. So we got U3 minus plus 1/2 times the state. So the eigenvalue has changed from U3 to this when acted on by t plus minus. So from this, we learned that U3 is changing like this, but from this, we didn't learn anything about how T prime and V prime is changing, how T and V are changing. For T, we have actually already learned this. Now, doing the same exercise for V3, we will find how V is changing when the state is acted on by V hat. So, putting together these pieces of information, what we learned from the V operator, what we learned from with respect to the U operator, and what we first learned, the standard case from SU2 for the T operator. Putting all that together, we see we can find the overall change of the state when we act on it by T hat. So T is increased or decreased as expected, but actually also U is changing when acting with T hat, and V is changing when acting with T hat. This we can explore graphically. So if we draw an axis with the eigenvalue of T3 going in this direction, then if we have states that are separated by 1 unit, so this is in a sense 1 unit big and this is 1 unit big, we have along this line our ordinary SU2 algebra. However, we see that when we have acted with T plus, so when we have gone in that direction in T space, we have actually increased V by 1 unit. So V has increased to V3 plus 1/2. So taking 1 step in that direction, we take half a step in the V direction. That means that the V direction must be separated by an angle of 60 degrees. So now we have locked the V line compared to the T line in this plane. We also see that when we take 1 step in the U direction, we actually decrease U with minus 1/2. So the projection of the change along the T line onto the U line plus p minus 1/2. And in this way, we lock the direction of the U line here. So, knowing the step operators, p plus minus, u plus minus, u plus minus, we will then be able to walk around in this two-dimensional eigenstate space or weight space with the weight of the t and v and u operators. We will have three such. We can talk about three such different states: the t and u and the v, three eigenvalues. However, only two of them will be independent. And it's time to stop here, but next time we will then sort of walk around in this multiplet space and we will see how the different multiplets in SU3 can be characterized in a way similar to the SU2. We will find that we can have multiple occurrences in the direct product space, and we will see some examples of some simple representations. But now it's time to stop, so let's first see if we had any questions to this or to anything else. Okay, if there are no questions, I should just say that next time we're finishing this up and we are moving on to something quite entertaining, that is the Lorentz group. And then I say thanks for today and bye for those who want to leave. And I'm staying on here for a few minutes to see if someone has some more semi-private questions to ask. So, yes, I don't hear any questions. I'm finishing this up and I say